Welcome, everyone. I have the pleasure of introducing Professor Surjeet Rajendran. I had the distinct pleasure of going to grad school with Surjeet. Unfortunately, I have nothing about those years that I can share publicly with you about Surjeet. So I'll let Andrew do the introduction, but you can talk to me privately.
Thanks, Mustafa. I don't have any fun stories about Surjeet at all, but I'm here to sing his praises for him. So Surjeet Rajendran is coming to us from Johns Hopkins, where he's been associate professor the past 2 years. Surjeet is one of these dynamic young people who makes bold claims and backs them up with detailed calculations. And so he's got a long track record of kind of pushing the field forward in order to come up with novel strategies for probing new physics. What we're going to be hearing about today is his work on searching for gravitational waves with a variety of techniques, including atom interferometry, which I think we'll be hearing about, and maybe some stuff about space. But he's also got other claims to fame. He's been interested in searching for axion-like particles with a strategy that's like nuclear magnetic resonance. It's called CASPR. He's worked on laboratory probes of dark matter. And what is it? Sorry, I had a list over here. Let me consult the list, which I hastily put together. Yeah. So for instance, the DM radio experiment, which some of you may have heard about last week in the Bonner Lab seminar from Josh Foster, who's working the Abracadabra experiment, which is somewhat related. He's also been doing more fundamental theory work, so he's been very interested in solutions of the hierarchy problem, explaining why is the Higgs mass so much lower than, say, the Guts scale, rather than inventing new particles at the weak scale to solve this problem. He's been proposing cosmological solutions using phenomenon of back reaction, cosmological relaxation. So if you want to feel relaxed, you can ask Surjeet about that. What else has he got going on? So I guess I should mention before he was at Hopkins, he was at Berkeley for a few years as assistant professor, and earlier he did his PhD with Mustafa, at Stanford. There's a fun fact about Surjeet, which I have recently learned and then need to bring to your attention. So apparently Mustafa taught Surjeet to drive, and then it took him about a year until he could get his license. I'm not really sure why that was. But anyway, thanks very much for coming, Surjeet.
All right. Thank you so much for inviting me. It's a real pleasure to be back and doing physics with people. It's great to see people in person, of course. So I'm going to talk about ways to open up the gravitational wave spectrum. All right, so what do I mean by that? As far as I'm concerned, right, the discovery of gravitational waves is one of the most interesting and exciting things that's happened in my lifetime in physics. If you think about it, it's for all the right reasons. Everything we have learned about the universe so far, mostly what we have learned about the universe so far, comes by observations of electromagnetism. And it is in fact the case that anytime we have looked at any frequency band in electromagnetism, we have discovered new things. Whether this was Galileo looking up with his optical telescope at the moons of Jupiter, or more recent observations of things like gamma ray bursts from gamma ray detectors, right? It is in fact the case that the universe has a much more varied phenomena happening than what we can dream of in our philosophies. That's just a fact about the world. So it's very interesting to ask what might be possible when we try to open up the gravitational wave spectrum as well. What could we actually see? The interesting thing about this situation is that we already know of known sources of objects in the universe which are bright sources of gravitational waves that we already know exist, right? So canonical examples of these are things like the mergers of black holes. Black holes don't emit much light, hence they're called black. Obviously, they are strongly coupled to gravitation. So a good way to understand the physics of what may happen in a black hole is, in fact, through gravitational wave mergers. There are also objects such as the mergers of compact stars, such as white dwarfs and neutron stars, that aren't particularly bright electromagnetically, but may indeed provide a lot of gravitational waves. So if you want to understand more about the progenitors of some of these systems, gravitational wave observatories are a good way to do that. And very importantly, gravitational waves are likely to play a fundamental role in expanding our understanding of cosmology. Because if you think about cosmology, we've already learned a lot about the early universe by looking at the cosmic microwave background. Detailed studies of the cosmic microwave background have been incredibly important in establishing the standard lambda CDM model of cosmology. But as you go back in time, it is in fact the case that any signal that comes earlier than, let's say, 0.3 eV or something like this, we can't get that in electromagnetism because of the fact that the early universe was just too hot and too strongly coupled to allow photons to go through. So 0.3 eV is not that high a temperature given the fundamental scales of particle physics. So if you want to understand really what happened in the very beginning of time, you require a new messenger to get to you, and that's going to be gravitational waves. So I'm sure you've heard all these spiels before, right? So to me, none of this really, I think, summarizes how important this discovery is. To me, what this really means is that, right, if I look at the last several years of our life on planet Earth, things have been pretty chaotic and crazy. Lots of things have happened. No matter which political persuasion, whatever it is you are, you'll find examples of craziness. But if you ask, what is it about our time that people will remember 1,000 years from now? It's not going to be any of this bullshit. It's going to be LIGO, right? This is really at that level because you know this. If you look back at the history of time, what do we remember about the time of Galileo? There were clearly all kinds of things happening. But what we remember is Galileo building a telescope, right? So this is clearly one of those scientific accomplishments that is so rare in human history that I suspect we will be learning things about gravitational waves for centuries to come. Right? It's very, very exciting. So LIGO opened up this game with their historical discoveries, trying to find gravitational waves between 10 hertz to kilohertz. That just happened a few years ago. Obviously, there's an interesting question asking, how can we find gravitational waves in other frequency bands? So if you think about this, you know, the way you build a telescope depends a lot on what frequency you're trying to go after. The way you build an optical telescope is very different from the way you build a gamma ray detector. Similarly, the way you build a gravitational wave detector that operates at different frequencies depends a lot on what is there at those frequencies, how those frequencies interact, the technology that you actually have to find it. So this talk is going to be aimed at that kind of view. What kinds of techniques can be used to find other frequencies of gravitational waves? But no matter what frequency of gravitational waves you're looking at, the fundamental physical effect of the gravitational wave is the same thing. You basically take two objects, you separate them by some distance L, the gravitational wave comes by, and it will cause the distance between the two objects to modulate back and forth. And the whole point about gravitational wave detection is that you want to measure the length modulation that is caused by the gravitational wave. If you can do that, you have found gravitational waves. The reason why this took LIGO 40 years and incredible amounts of effort is precisely because even if you think about the brightest sources of gravitational waves in the sky, they are extremely weak effects in terms of what we as humanity can normally deal with. So at LIGO, for example, they need to measure length changes of order 10 to the minus 18 meters, 1/1000th the size of an atomic nucleus, to be able to see gravitational waves at those frequencies. So fundamentally, to see gravitational waves, what you need are a combination of two things. You need precision sensing, right? You need some technology in the world that will allow you to measure such a small number. But it's not just the fact that you have this precision, you also need stability. So if I take these two objects and I separate them by some distance, it is not sufficient for me to be able to measure their distance to the accuracy of 10 to the minus 18 meters. I also have to make sure that these two objects, they are part of the world will try to move them back and forth due to a variety of noise sources. So I have to come up with a way in which I can decouple these two objects from the environment to this incredible level of accuracy. If I don't do that, I'm swamped by noise. So the technology you want to think about basically needs to solve both of these problems. I'm not the first person in the world to say there are gravitational waves at other frequencies. There are already many other efforts underway to find gravitational waves at other frequencies. So here is the plot that I stole from the internet. And this is a plot in characteristic strain, which is the amplitude of the gravitational wave. That's what's there on the y-axis. And on the x-axis is the frequency that you're in. So what is plotted here is basically various expected astrophysical sources, right? We know some things about what's out there in the universe. Supermassive black holes, white dwarfs, all these kinds of things. And that's what is plotted here, where you expect the astrophysics to lie. And overlaid on top of that are various detectors. So for example, if you look at LIGO is sitting somewhere out here, okay? They need to detect characteristic strains of order 10 to the minus 22 at around, let's say, 100 hertz. That's what they did. That's why they're in business of finding gravitational waves. There is a LISA experiment, which presumably will get built, and that operates at around millihertz or so. And they're looking at gravity waves at a characteristic strain of around 10 to the minus 20. Okay? And then there are these pulsar timing arrays. That's an experiment that already exists. They've made a lot of progress, and there's even some claimed detections, possibly, in pulsar timing arrays. And they operate at frequencies of around 10 to the minus 9 hertz. They're called nanograv because of nanohertz, and they're operating somewhere out here. So if you look at this plot, there's an interesting fact, which is that if you want to go to the right of this plot, what you realize is that you need to go and build more and more precise instruments, right? If you look at what are the sources of gravitational waves that are dominantly you're going to see out there, at higher frequency, you are basically required to have much better precision, right? You need much more precision to see these very, very weak effects. 10 to the minus 22 is a characteristic strain that you're actually probing, okay? But as you go to the left of this plot, okay, somewhere out here, let's say at nanograv frequencies, notice that the characteristic strain you are measuring is many orders of magnitude larger than the characteristic strain that LIGO wants to see. So that's more like 10 to the minus 16 as opposed to 10 to the minus 22 or something like this, right? That's because fundamentally these events that you're looking at these low frequencies are incredibly violent events. They have to do with the mergers of extremely massive black holes that are putting in a gigantic amount of energy out into gravitational waves. So the intrinsic strain that you're looking at here is much larger. Looking at that plot, you might say, well, why did these LIGO guys choose to build LIGO over here, right, at this very, very high precision, as opposed to trying to do something at this lower level? The point is, of course, the issue of stability. It's not just your ability to measure a tiny effect. It is also the fact that whatever two objects you're considering have to be decoupled completely from the environment. Now, LIGO operates at around 100 hertz or so, where basically if you take two objects, separate them by 4 kilometers or so, they're hung from some very complicated vibration isolation systems. So when the world shakes at frequencies of around 100 hertz, it doesn't vibrationally affect the mirrors. But as you go to lower frequency, if you try to do the same thing, what you're going to find is that the very large amount of noise that exists in the world at low frequency will couple into your detector, preventing them from seeing it at low frequency, right? So you see that the key point here is that as you go to lower frequency, what you want are, the problem really becomes much more an issue of stability, because the fact is you have to decouple your proof mass, whatever it is you're using to detect the gravitational wave, from any kind of environmental activity. And of course, 10 to the minus 7 hertz, 10 to the minus 8 hertz, these are like year-long timescales, right? Lots of things happen in the world over a year-long timescale. So how do you build two objects that don't move very much over the timescale of a year? So it's that kind of thing you want to think about. So with that, let me talk about the three opportunities that I think exist if I look at this plot and see where progress could be made, where new ideas are necessary. If you look at the gaps over here, there's a gap somewhere out here between, let's say, 1/10 of a hertz and about 10 hertz. And I'm going to propose the use of atom interferometers to find gravitational waves in that frequency band. Then the next big gap is basically between nanograv and LISA, this frequency band. And I'm going to talk about two different ideas on how to probe that combined parameter space. The first would be to the use of ranging asteroids, okay? That's between a microhertz and about 0.1 millihertz. And between 10 nanohertz and a microhertz, I'll talk about the use of astrometry, measuring the positions of stars very accurately. In terms of how on-shell these projects are, it's also in the same order, where the stuff with atom interferometers has taken many years. There's lots of activity going on these days. The other two things are much more recent. Let's talk about atom interferometers. First of all, what is the science case? Why would you want to go and build a gravity wave detector between 0.1 to 10 hertz, right? So one of the main reasons why you may want to do this is because you may want to actually go and look at the mergers of white dwarfs. So we know white dwarfs exist in the world, they merge. When they do so, they produce type 1a supernova. There's a long-standing question of what is it that actually are the progenitors of type 1a supernova that we see. Some of them may be due to white dwarf mergers. And these white dwarf mergers occur all the time, presumably, and they can never be seen at LIGO. This is because of the fact that if you think about what's happening, I have two stars that are going around each other, and as they're far away, they're at low frequency. As they emit gravitational waves, they fall into the orbit, they go faster and faster and faster. So if you look at the in-spiral of a star, it starts with low frequency and walks up towards high frequency. But the highest frequency it gets to is basically set by the size of the star, right? Eventually, the highest frequency they can get to is when the stars collide. A white dwarf is 10,000 kilometers or 6,000 kilometers in size. So the gravitational waves produced from its merger, they basically exist between 0.1 to 1 hertz. They will never make it to the high frequency band of LIGO. So you want a detector at these low frequencies to see these. The second thing is you can look at your canonical, it's funny to call anything canonical when it's only been discovered a few years ago, but say the canonical LIGO sources, right? So LIGO sees these black hole mergers. So if you think about what's happening in these mergers of these black holes at LIGO, again, right, they're sort of starting at low frequency, they spend a long time going around each other, and as they infall, they get faster and faster and faster, and eventually they merge in LIGO. So a source in LIGO typically lasts only about a few seconds, okay, and then it merges. While at low frequency, at say 1 hertz or so the same source, right, the same source that LIGO sees, when it's seeing it at merging at, whatever, 10 hertz, it of course spent some time before that going at lower frequency, before it wobbles, before it spirals into the high frequency. So that LIGO source, when it used to be at 1 hertz, it spends about a week going around the other star before it slowly spirals and becomes the LIGO source that you see. This 1 week that it spends at low frequency is very important. First of all, you often want to know which part of the sky the event came from. You want to do angular localization. The way you do angular localization in a gravity wave detector is basically by doing triangulation. You build, a couple of detectors and you see if you can, do some time correlation to figure out where the event came from. Anytime you're trying to do angular localization, you want your detectors to be as separated in space as possible. This is why LIGO, for example, wants full Earth coverage by having detectors in India, Australia, places like that to get the full coverage. But in LIGO, these sources only last a few seconds, so essentially that's the most they can ever get in terms of angular separation. But when your source lives for 1 week, in 1 week, the Earth travels a gigantic distance around the solar system. So when you have a detector that is able to look at a LIGO source for 1 week, you're effectively getting a very, very large baseline to do your angular measurement simply because of the distance that the Earth has traveled. And therefore, these instruments, if you're able to build something at 1 hertz, you will be able to get essentially degree scale localization of these events in the sky, or sometimes even better than that depending upon the SNO. Secondly, 1 week is a long time to go and tell all of your friends who have electromagnetic observatories, like gamma ray telescopes, optical telescopes, whatever it is, and be like, guys, 1 week from now, there is going to be an interesting event in that part of the sky, go point and look at it, right? So if you want to do multi-messenger astronomy, stuff like this really becomes extremely helpful to have a detector at this frequency band. The final reason why this is a very, very interesting band is because this band is also extremely interesting for cosmology. So if you're interested in physics of the early universe, like inflationary cosmology typically produces gravitational waves with a very flat power spectrum. That basically means at every frequency band, the amount of energy density is pretty much the same. So it's got a formula like this. Omega goes as h squared omega cubed. H is the amplitude of the gravity wave. Omega is the frequency. So for a flat spectrum, like inflation, this formula basically tells you that the amplitude of the gravity wave is inversely proportional to the frequency to the 3/2 power. Now notice that gravity wave detectors we are trying to build dominantly respond to the amplitude h directly. That's what you're actually measuring, the direct strain. What this means is that for a given inflationary source, right, some primordial source, the source has a larger amplitude at lower frequency, right? At higher frequency, it's much harder to detect because essentially if you look at this equation, that's what it says. So if you want to detect something primordial, you want to go to the lowest possible frequency. So you might say, well, why not go to the very, very low frequencies where the amplitude would be gigantically larger? The problem is, as you go to lower and lower frequencies, you start realizing that all the white dwarfs and other stars in the world are also going around each other at low frequencies. So they provide a large stochastic background in gravitational waves to these primordial gravitational waves. Okay? So it turns out that the best band to do these kinds of cosmological measurements is actually between 0.1 hertz to 10 hertz, because 0.1 hertz is somehow high enough that there aren't that many white dwarfs over there because they're already merging, they're not doing very much. Okay? At the same time, so below 0.1 hertz, you're completely swamped by astrophysical backgrounds of gravitational waves. And so essentially the fact that you want to be at the lowest possible frequency basically tells you that you want to do something in between 0.1 to 10 hertz. So why can't LIGO do this, given that there is a very strong science case for going after this frequency band? So let's think about how LIGO actually operates. So the way LIGO actually operates is that you take a couple of mirrors, right? You separate them by 4 kilometers, you send a laser through these things, and essentially you're measuring the distance between these mirrors using an optical interferometer, and that's the basic idea of LIGO. And the problem with LIGO is that when these mirrors of LIGO, they're held to some ceiling, and when the ceiling is held to the ground, and when the ground wobbles due to seismic activity, the ceiling wobbles, and that will cause the mirrors to also wobble. So they have to hang these mirrors from some of the world's best vibration isolation systems. And even though LIGO does incredible work, it is simply the case that the amount of activity that exists in the world below 10 hertz rapidly prevents their ability from making any progress at all in gravitational wave physics below 10 hertz on the ground. So what can we do that will circumvent this problem? So that is the idea of this MAGIS experiment. Okay? I forget what that acronym stands for because it's changed depending upon how we can get our money. But it's always remained MAGIS. Right? So here is kind of the concept. Imagine you could do the following, right? Imagine I could take the mirrors of LIGO and I drop them, okay? As they're falling, suppose I measure the distance between them with an optical interferometer. So I take 2 mirrors, I'm dropping them, they're in free fall. As they're in free fall, I measure the distance between them. Of course, a gravitational wave will come in and will modulate that distance as the mirrors are falling. So if you're able to measure that distance very accurately, you will of course see the gravitational wave. And now when the world shakes, since these mirrors are in free fall, the vibration doesn't directly couple to them, right? I've basically built you the world's best vibration isolation system because I'm not hung from the ceiling. Of course, this is ridiculous because nobody is going to let you drop a 40-kilogram sapphire mirror just to find a gravitational wave. That's ridiculous, right? So the question is, what can you drop that is very cheap to drop, at the same time, very precise? Atoms, ultra-cold atoms. That's what we want to drop and make this measurement. So how does this work? Okay, so here's a cartoon, and then I'll tell you the technology step by step. So here is how it's supposed to work, okay? We're going to find a kilometer-long mine shaft, okay? Somewhere, a vertical kilometer-long mine shaft somewhere in the world. And what we're going to do is drop a bunch of ultra-cold atoms at the top and a bunch of ultra-cold atoms at the bottom. And as these atoms are falling, we're going to measure the relative acceleration between these atomic clouds very carefully using atom interferometry. We will talk about how that happens shortly, okay? And that's what we want to do, because now if a gravitational wave goes by, there's going to be a relative acceleration between this atom cloud and that atom cloud that your atom interferometry should pick up. At the same time, if the world shakes, it does not directly vibrationally couple to your atoms, and thus you vibrationally decouple. So how does this magic technology work? How can I measure this incredibly small length change or a very, very small time change, right? That's what you need to do in order to measure this small effect. So let's talk about what an atom interferometer is. This is a space-time diagram for the atom interferometer. There's time here and space over here. So here's what we're going to do. We basically think about the fact, at say at time t equal to 0 or so, we have some atom. This atom is in some initial momentum state p. Okay? That's just what happens here, time t equal to 0. And at time t equal to 0, so I took my atom that was in some initial momentum p, and by a magic operation called a beam splitter, I'm going to place it in a quantum mechanical superposition of half the atom with momentum p, the other half has gotten a kick, p plus k. Okay? So through the magic of quantum mechanics and this magic beam splitter, I've created that quantum state. And then I let the system time evolve. As I let the system time evolve, these two guys will pick some relative phase between them. And then at time t, by another magic operation called a mirror, I'm going to swap these momenta. So the guy that used to move with momentum p now gets a kick. He goes with p plus k, and the guy that is moving with p plus k goes with p. So in this space-time diagram, what happened is that this is the state with p, he became p plus k. This is the state that was p plus k, he becomes p. So these guys will now come back to the same point in space-time, where there's now some relative phase between these two arms of the interferometer, if you will, and I want to read out that relative phase. What I do is I apply another final magic thing called a beam splitter, which takes this p plus k to this linear combination and this p to that linear combination. Okay, this is some simple quantum mechanical algebra. There will be no test on this. So if you do all this algebra, what you see is that at the end of the day, when I performed all of these operations, that phase, e to the I delta phi, which you wanted to read, it becomes this quantum state, okay? After all this has happened, it is 1 plus e to the I delta phi in momentum state p, and 1 minus e to the I delta phi in momentum p plus k. That's just what happens when you do all the algebra. To measure this phase, what you're going to do is you're simply going to count, at the end of the day, how many atoms end up in momentum state p, how many atoms end up in momentum p plus k. You're just taking photographs and asking how many in p, how many in p plus k, and that depends upon the exact phase delta phi. That's roughly how it works. So to convert this conceptual point into an actual physics thing, I have to actually tell you how did the fancy thing called the beam splitter work? How did that magic of the beam splitter actually work? And here is how it works. You take an atom that is initially in some ground state of the system and has got some momentum p. And what you do is that you find very special kind of atoms, okay, strontium, mercury, things of this kind. These guys have a very special property that they have excited states of these systems which are split by 1 electron volt. So they're like pretty, like a first excited state. Typically, your first excited states, they decay very quickly. But in these systems, the first excited state lives for something like 1,000 seconds or longer. Okay, this has to do with the fact that these transitions are extremely forbidden. So they don't decay that quickly. What that means is basically that you can take your atom that is in the ground state of the system and has some momentum p, and what you do is you apply a laser pulse, let's say from the left over here. When you do that, this atom will go from the ground state to the first excited state, and in doing so, by absorbing this photon, it gets a momentum k, which is the momentum of the photon, a 1 eV kick. It's gotten a kick to the right because of this. And this technology is what is actually used successfully in optical atomic clocks, by the way. Now, we want to separate these atomic clouds as much as possible because the more you separate them, the larger the signal will be in our setup. And how do you do that? How do yes, sir?
Why is it important to have a single photon transition and not just drag?
This comes down to how you cancel laser phase noise. So I will show you, ask me that question in a couple of slides and I'll tell you how to do that.
Surjeet, just to clarify, if this transition is optically prohibited, why would it absorb photon?
Oh, it's just a question of intensity and going on resonance, right? That's basically the thing.
No, but if the transition is prohibited, it's going to spend about 1,000 seconds before it absorbs it by the same law.
No. It's like it's a fact that you're actually. So a couple of things. So there are some forbidden transitions where you can actually apply a little magnetic field to make it a little bit of a mixing, which will make this happen more quickly. So that is one possible thing. The other thing is also the fact that these are actually, I shouldn't have said the word absorption. I actually mean something coherent. So this is like more like a Rabi flop where I apply a large electric field from the laser. And it is that pulse intensity which actually drives it as well. Okay. So what I want to do is I want to kick this atom many, many times, right? I want to kick it lots of times. So I'm going to start with ground state in 1p, and it goes to the excited state. That's what we said. I've kicked the atom from the right here, so I got a kick to the atom to the right. What I can now do is I can smack the atom from the left with a counterpropagating laser light. And what this laser light will do is that it actually causes stimulated emission of the atom to go from the ground state, from the state 2, metastable state 2, to the ground state. So that is stimulated emission. So when you do stimulated emission, what that means is that since this photon is coming in from the left, the stimulated emission photon will also go to the left, which means the atom will now get a kick to the right. Okay? So this process basically starts with atom in momentum state 1, goes to 2, and when I do this kick from the left over here, I end up kicking the atom to the right again. Okay? So I've essentially gone from P plus 2K that I had to P plus 3K. Okay? And now I keep sort of repeating this process many, many times. Right? So as I repeat this process many, many times, I will be able to deliver more and more momentum to the atom. So here is the space-time diagram for this, which is the fact that here's my atomic clouds over here that was initially at time 0 or something. At time 0, I pulse one of these lasers. It goes and hits this guy. It does the first kick, right? So this was in the ground state. It now becomes the first excited state. I got one kick. So that was my absorption from the right. So the atom got kicked to the right. Then at time, as soon as this photon comes here, I send another photon pulse from another laser going to the left. And now what's happening is that this guy undergoes stimulated emission from the left, which basically means the atom gets kicked to the right again. So this way, by driving this transition many, many times, I can create a large separation in the physical wave packets between these two things. Okay? And notice that any time I actually have the atom in the excited state, I can use that as a way to measure time, right? Because when these two guys are in two different atomic states, it'll be the case that there's a relative phase between them because there's an EV scale energy difference between these two states, and that can be used to keep track of time. So let's think about this protocol abstractly before we get into the details of the atom interferometer itself. Here is what this protocol is going to do. I can think about two clocks. I have one clock here, and there's someone else with another clock very far away. Say Mustafa's taken another clock and gone very far away, right? And I'm going to sit in this clock, and I'm going to send laser pulses to Mustafa every, say, t seconds. So at time t, 2t, 3t, I send these laser pulses. And Mustafa receives this, and he simply measures the arrival times of these pulses. So if I send the laser at pulses at time t, 2t, 3t, if nothing is going on, there's no gravitational wave, Mustafa will see them at times t plus L, 2t plus L, 3t plus L, so on and so forth, where L is a separation between the two of us. But if a gravitational wave comes by, even though I'm sending these signals at time t, 2t, 3t, so on and so forth, since the space between us has expanded or contracted, the arrival times that Mustafa measures will change from t plus L to t plus L plus epsilon, 2t plus L minus epsilon, so on and so forth. There is going to be a modulation in the arrival time of these pulses, and that is what we are actually measuring in our experiment. So I'll now answer the question that you raised. Why am I doing this using single photon interferometry as opposed to the more conventional sort of like Raman spectroscopy, Raman interferometry? That's for this reason here. It's what is called a single baseline gravitational wave detector. If you think about LIGO, not only did LIGO have to come up with a way to isolate their proof masses from any kind of environmental noise, they also had to make sure that their laser noise was small enough, right? Because you are at the end of the day measuring the length between two objects. That can change due to two reasons. The objects themselves moved, either due to some noise or due to gravity waves. The second is that the objects may not have moved, but let's say the laser frequency drifts back and forth. The laser frequency drifts back and forth. That is a ruler you're actually using to measure the distance between these two objects, and that of course will change. So even if there is no actual length change, if your laser frequency drifts, that will also show up as a gravitational wave signal. So what LIGO does to solve this problem is that they create two arms, right? You've seen the picture of the L shape, and that is because they send the same laser through both the arms, and since the laser frequency noise will be common to both the arms, when the laser frequency is recombined, that noise goes away. The gravitational wave causes a contraction in one side and an expansion on the other, so the gravitational wave signal does not go away. So that's how LIGO solves that problem of laser phase noise. What do we have here? How do we combat laser phase noise? We combat laser phase noise because we'll have the same problem, right? When I send this laser out here, this laser has a frequency, and that frequency could be noisy, it could be drifting. But notice that the same laser frequency, whatever it is, gets put on this atom and that atom. Because the same laser pulse that drives both transitions. Because the same laser pulse drives both transitions, when I take my differential measurement between these two atom clouds, that laser phase noise will get cancelled. Now, for the people who are more technically knowledge, right, if you try to do this using the Raman thing, you're going to find there will be some level at which the laser that you use to drive from this guy will not be common. So you're going to have uncancelled laser phasors. That's why we use single photon interferometry, because we're going to use the same photon to drive both these transitions. So it turns out laser phase noise is cancelled by doing this up to small velocity corrections. And you can really just think of this as a comparison of two distant atomic clocks in the presence of a gravitational wave. And because I completely cancel laser phase noise in this particular way, this cancellation scheme relies solely on the fact that the speed of light is constant going from here to here. So it's like a fundamental thing that's really anchoring this comparison over here, as opposed to something like a laser frequency drifting. So here's how the setup is supposed to work. I kind of briefly put the cartoon up earlier. So we're going to find a kilometer-long mine shaft somewhere in the world. We're going to put two atom interferometers. Each of them will be they'll spatially go up and down by about 10 meters or so. One at the top, the other is at the bottom. And they're going to be operated by common lasers from the top and the bottom. The lasers are going to go up and down doing all the atom interferometry. That's how you run it. The signal in this experiment now scales with the separation between the interferometers. So with a kilometer-long separation, you get a kilometer-long baseline. And if you ask what frequencies will we be maximally sensitive to, essentially it takes the atom about a second to go up and down 10 meters. And that will basically mean that this instrument is maximally sensitive to gravitational waves in the 1 Hz frequency band. So this thing has gotten ahead quite a bit. MAGIS, this is the original proposal, and all these things were worked out for, basically has a bunch of cash now from the Moore Foundation as well as the Department of Energy. So there is a 100-meter proof of concept facility being constructed at Fermilab using the old Minos shafts, where they're going to basically put up a couple of interferometers at the top and the bottom and show that this kind of cancellation actually works, that you can run these multiple atom transitions and all that stuff, right? So that's only a proof of concept. It doesn't actually get you to a full kilometer scale gravitational wave detector. But should all these techniques work as we hope they would, we will then be able to have a strong case to say, give us the money to build a kilometer scale experiment and do things. There are also a bunch of other people who have now signed on to these efforts. There is MIGA and ELGAR. These are efforts in France. They're funded at some level to do some of these things over there. There's also Aeon in the UK, and I believe Zyga is a Chinese experiment that has been trying to do this as well. Okay. So lots of acronyms. So I'll just tell you about what I know is happening at Stanford, because those are my friends. And this is Jason Hogan and Mark Kasevich, who have been doing this for quite some time. And it all really started with their interest to measure the equivalence principle. So they wanted to drop rubidium-85 and rubidium-87 and see one falls faster than the other, right? They were going to do Galileo's experiment. But over time, that experiment has gotten more and more ambitious in trying to go well past the equivalence principle limit. That's not their primary motivation now. It is really more to look at these gravitational wave things and serve as a proof of concept for several of these things. So what have they demonstrated in the lab so far? So what they've demonstrated in the lab so far is that they have basically gotten phase sensitivity at the level of 10 to the minus 4 radians per root hertz. And these multiple photon kicks that we talked about, right? Like I'm going to drive the atom interferometer from the left and the right, the left and the right again and again. They have done it 100 times, 141 times, okay? They've split the atoms by 141 photon recoil. That's been demonstrated in the laboratory. They've also done a little bit of spin squeezing, although we don't, squeezing to get a little bit of better sensitivity, although we don't really usually think about squeezing as something necessary for a gravitational wave setups. This is just what they have demonstrated in their lab. And part of what we are funded for to do in Fermilab is to integrate all of this in the 100-meter apparatus and see if it all works at the large scale as we hope it would. One can also do the same kind of thing in space as well, just to put that idea out there. What you can do is you can take two spacecraft, separate them by some long distance L, and pretty much do the same experiment, right? Like you have atom interferometer here, and you're going to measure the relative distance between them using interferometry, a lot like how you would do with an optical kind of interferometer. And the atom sources and the lasers all have to be in the satellite, so it's a lot like a conventional satellite experiment. And you can ask, what is the main limit on how far away you can separate these two things? A simple limit is basically that you want the same laser beam to drive both of these atomic transitions, and so you need to have enough power to drive the transitions. So if you have something like a 30 centimeter optical beam optic to send your light, you can go up to about 1,000 kilometers before you start losing photon flux. This is not a fundamental limit. You can do fancier things with something like heterodyne interferometry to separate them even further, but 1,000 kilometers is a pretty reasonable thing to do and still get interesting sensitivity. So this is the proposed sensitivity of where we think we can go. Roughly, I would say between 0.1 hertz to about 10 hertz, we hope to get somewhere along 10 to the minus 21. Now, to be fair, a terrestrial setup, even though we are able to get rid of the direct coupling of seismic activity by just dropping the atoms, this does not mean we are done with seismic activity, because here's what's happening, right? The atoms are in free fall. When the world shakes, they're not coupling to the atoms directly. But when the world shakes, gravitationally, those shakings will couple to the atoms, right? You can't screen gravity. So it turns out that as you go to frequencies below 1 hertz, this gravity noise, time-varying gravity gradient noise as it's called, also gets very big. So there's no way you'd be able to go all the way down to 0.1 hertz in a terrestrial setup. That's very hard. So somewhere below 1 hertz, we will be swamped by that noise. We don't exactly know where. It depends a lot on which site you use and things of that sort. But above 1 hertz, there's good reason to think that this kind of technology will be able to get to interesting sensitivity. So let me switch gears and talk about the next part of the talk, which is the potential of using asteroid ranging to try to detect gravitational waves between microhertz and 0.1 millihertz. So here's where we are in the the plot that someone made and I made modifications to. So we kind of talked about how if we're able to build these sort of atom interferometers at this mid-band frequencies, we will be able to see gravitational waves over here at the mid-band frequency 0.1 hertz to about 10 hertz. There's now an interesting question. LISA cuts off somewhere here, and the pulsar timing guys are somewhere there. So what can we actually do at microhertz frequencies? What's the challenge? So the question you really want to ask is basically, well, why can't LISA go to microhertz frequencies? What is it that causes LISA sensitivity to dramatically rise up at low frequencies? On the Earth, we know the answer. The reason why LIGO went up was terrestrial seismic activity, and then the coupling of the seismic activity to through gravity itself. But what is it that similarly blocks LISA? After all, they're in space. So the challenge of doing something like LISA is the following. Yes, you went to space, you don't have your typical seismic noise, but what are you doing in LISA? You're basically saying, inside my satellite, which has all sorts of complicated things, inside my satellite there are these proof masses, right, little cubes or whatever, and what you're trying to do in LISA is basically, I have one cube inside one satellite, I have another cube inside another satellite, and I'm trying to measure the distance between these cubes very, very accurately. These cubes are free-floating bodies, right? Now what happens is that this satellite, of course, is this big thing, and it's going to get smacked by all kinds of stuff. Cosmic rays, solar intensity fluctuations, charging of the proof mass, a whole bunch of things, which will cause that proof mass, the satellite itself, to wiggle. As a satellite wiggles, it can now drag the proof mass as well, right? So you have to decouple the random motions of the satellite from the motion of the proof mass. So that means you need to fly what is called drag-free, right? This is the technology that is core to what LISA needs, all right? And once you have a drag-free setup, you're once again just able to measure the distance between these proof masses and measure them. So that's kind of what LISA hopes to do. Now, how drag-free can human beings engineer something, right? So the LISA Pathfinder experiment, which is a heroic effort, and it took decades, 2 decades or whatever it is, flew, and it successfully did what it needed to do for the sake of LISA, right? So this is their result. What you see is that at millihertz frequencies, they've achieved what LISA requires. In fact, a little bit better than what LISA even required. But at low frequency, again, it rises up, right? That is because of the fact that there are a variety of things that will come in there and cause this satellite to wobble in uncontrolled ways, and then you're worried about how those uncontrolled motions will cause your proof mass to move. So this is what human beings have been able to do so far in terms of engineered masses that we can put in orbit and make them move that way. What could we possibly do to combat something like this? How could we go to lower frequency if somehow 20 years of work, this is where we are? Here's a thought, right? The problem of noise is that there is some force acting on a system, and that force causes an acceleration. Now, due to Newton's second law, we basically know that if I make the mass of the system much larger for a given force, the acceleration will be smaller. So if I could magically launch a very, very heavy satellite, these random motions will be much more controlled in terms of the position displacement they cause. But of course, I can't launch really heavy things in space, right? It's extremely expensive. So one thing is, what about natural objects? So after all, if I'm able to look at the center of mass position of the Earth, of a planet, right? The center of mass position of the planet Earth is extremely stable. Just because some cosmic ray comes and hits it and charges it or whatever, it doesn't wobble very much because the Earth is huge, right? But we can't use the Earth as a proof mass because on the surface of the Earth, all kinds of stuff is going on. We've got seismic activity, atmosphere, all kinds of stuff, which means that even though the center of mass of the Earth is very stable, its surface is very, very unstable. That was the first problem we were trying to deal with in trying to build things like LIGO. What about other natural rocks that are out there? Specifically, an asteroid, which is a few kilometers in size. The advantage of thinking about an asteroid is that an asteroid is big enough that its center of mass is pretty stable. We will talk shortly about how stable it actually is. At the same time, it does not have its own internal dynamics, right? It's a pretty small thing. It also does not have an atmosphere when it's at the level of a few kilometers. So one might think that asteroids should be pretty stable seismically, or at least you can find a class of such objects that have enough seismic stability. So does that idea make sense? Few kilometer scale rocks. So here is the concept. You find two asteroids, okay? And what you're going to be doing is you're going to, on each of them, you're going to put either a radio transmitter and a receiver. That's one option, or a laser link. And what you're doing is sending radio or laser frequencies from one asteroid to the other. And basically, you're doing like radar. You're doing ranging, right? You send signals from this guy to that guy. There's some clock here, and that clock will, this is the Mustafa experiment, right? Time t, 2t, 3t, and you see at what time this guy is received. The gravitational wave goes by, there'll be a wobble, a change to that thing. That's what you want to do. So the question is, how stable does an asteroid have to be for me to do this measurement? Does it have to be stable at the level of 10 to the minus 18 meters, which is what I needed for the case of LIGO? That, of course, I don't know how confident you will be that an asteroid is stable at the level of 10 to the minus 18 meters. But notice here, the interesting thing is that the gravitational wave strains we are looking at are much brighter at lower frequency than what LIGO was looking at. So I'm looking at gravitational waves with strains of around 10 to the minus 17 to about 10 to the minus 18. And these asteroids will be separated by something like an AU between them, which means that the length changes I need to measure are on the order of a micron to 0.1 microns. Okay? So what you care about is basically, is the seismic noise on an asteroid that causes its, well, both the center of mass fluctuations as well as random seismic activity, are they larger than 0.1 microns? That is the relevant thing. It's not 10 to the minus 18 meters, it's 0.1 microns. So before we get ahead, let's ask a couple of sanity check questions. Can we land on asteroids? Do we need to send an all-American hero like Bruce Willis to land out there and do some, amazing things? So the answer is, we don't quite need Bruce Willis. Humanity has successfully landed stuff on asteroids now for 2 decades. NASA's gone there several times, as have the Japanese, right? It turns out that landing on asteroids is not quite as scary as landing on a planet like Mars or something, because when you go to Mars, you launch yourself with a large velocity, and then Mars has a large gravitational field, so you have to slow down. This is the final minutes of terror that they always talk about. Asteroids don't have self-gravity. It's not very big. So you don't have to slow down. What you do is you launch yourself so that when you get to the asteroid, the relative velocity between you and the asteroid is pretty small. So you can kind of do a pretty gentle landing on them. So that's kind of how they do these things. The second thing is, what about atomic clocks? I needed to launch this thing with a good clock. Do I need a fancy clock like the one that we're trying to build for MAGIS? Turns out that we are looking at stability for the clock at the level of 1 part in 10 to the 17 or 1 part in 10 to the 18. So these are clocks that the guys in NIST build on planet Earth. Okay? These are not space qualified clocks, right? So that's obviously a much more difficult and newer thing. But at least at the level on the surface of the Earth, these clocks are not insane. They already exist. So the question now becomes really one about, is it really the case that the surface of the asteroid and its center of mass are stable enough? Okay? What do we know about these things? So we've gone through a bunch of these noise sources. A lot of the knowledge on this really comes from the fact that people put seismometers on the moon and Mars, more recently on the Mars and before that on the moon. And we do see seismic activity. in these kinds of planets, in the moon, for example. And the sources of them on the moon, for example, are things like the fact that the Earth tidally acts on the moon. It's also the case that when you have rotation of the moon, which the moon does rotate and has really no atmosphere, when you go from the day of the moon to the lunar night, you're going from extremely hot temperatures to extremely cold temperatures and back and forth. So at those frequencies, you do get cracking of the moon. So these things that are actually been measured. You also get some level of seismic activity from just impacts, stuff hitting the moon. So we've run these kinds of numbers on the asteroids as well, and we find that these are the dominant noise sources on what would cause both the center of mass of the asteroid to fluctuate as well as the seismic activity. So the dominant ones turn out to be basically solar intensity fluctuations as well as the fact that the solar winds fluctuate as well. Okay, these both turns out to be roughly comparable to each other because the solar intensity, of course, is much larger, but its intrinsic fluctuation is a lot smaller. The solar wind is lower in intensity overall, but it fluctuates by large amounts. Also, we have a bunch of noise, of course, at the rotational period of the asteroid, because that's when it faces the sun and moves away from the sun. So you will get thermal cycling, etc., focused over there. All right. I will talk about this noise shortly. Okay, so this turns out to be a fundamental noise that we discovered in doing this particular analysis, which is coming from the fact that when I have these asteroids, and I'm trying to measure the distance between them, there are millions of other asteroids in the solar system, and as they are going around, they will exert gravitational forces on these asteroids and cause them to move back and forth. So there's going to be gravity gradient noise from the million asteroids in the main belt as well, and we computed that specifically to talk about it. So I can tell you offline how these calculations are done or estimates are done, but bottom line is that none of these things seem to be too problematic at the level of order of magnitude estimates. We've also looked at measurements of seismic activity at the moon as well as Mars, and the quakes that you see are not above tens of nanometers. So they're not quite at the 0.1 micron or micron level. Of course, seismic activity is measured at higher frequencies, right? Because that's kind of where these wobbles happen. Not quite at the low frequencies that we want, but it's all encouraging, suggesting that nothing crazy is really expected. And ultimately, of course, you require the ability to run the experiment, radar ranging, whatever it is, so you get like link noise, laser frequencies, stuff like that. So what we believe is that if you look at these variety of noise sources, which my postdoc has gone through in great detail, we believe that actually between 10 to the minus 6 hertz to about 10 to the minus 4 hertz or so, asteroid intrinsic noise is small enough. Okay, that's our estimate. Small enough that one should be able to do this kind of ranging and see interesting gravitational waves. Now, I am not suggesting that someone give me $1 billion to go and put atomic clocks and radar ranging and all these things on an asteroid based on my ability as a theoretical physicist to do order of magnitude estimates. Okay, I'm a confident man, but I'm not that confident. So what we are really hoping for, right, is that the next time someone goes and lands something on an asteroid, take a seismometer with you, okay? Try to make some in situ measurements and see if in fact these rocks are stable to the level of 0.1 microns. What you really want to do is basically, I think, like land in a couple of places in an asteroid, and this has also been done because since they don't have a large self-gravity, you can land in one place and then go land somewhere else. Land in a couple of places and then create a little link between these two places and see if these two places are moving away from each other due to any kind of activity larger than 0.1 microns. Right? So if that happened, of course, okay, my order of magnitude estimates were worse than I thought they were. But if it worked, then you might follow up and do a real mission where you land there with all the atomic clocks and radar ranging and things of that sign and see what you can do. So we believe this strongly motivates a in situ apparatus to actually go and do seismology on asteroids, which may be interesting for people who want to study about asteroids anyway, right? I think that's a cool thing to study. And also interest in trying to detect, to create space qualifying cold atomic clocks, which don't exist right now, but I think there's a lot of interest anyway in the community to build these things. I think this sort of gives extra impetus to do things like that. So let me try to now move to the last part of my talk, which is why am I talking about astrometry? What is it that prevents these asteroids from going to even lower frequencies, right? Why do I want something different between 10 nanohertz to 1 microhertz? And that is due to the following fact. we live in the inner solar system, and there are things in the inner solar system like the sun, planets, and all these things, as well as asteroids. Now, when the planets go around each other, go around the sun, and I have, let's say, a couple, and let me think about a very LISA-style experiment, where I take two proof masses in the inner solar system. I'm trying to measure the distance between them very accurately. Of course, as the Earth goes around the solar system or Mars goes around the solar system, they will, of course, act on these proof masses gravitationally, causing them to move back and forth, right? So that is a source of noise, if you will. But we know what these planets are, right? So since we know what these planets are, there's only a small number of them, we can subtract that out. So that's not noise, because we know lots of properties about these things. But it is also true that we have a million asteroids in the inner solar system, sorry, in the main belt over there. And these guys, we know very little about them. Generally, the masses are very poorly known, indirectly determined. Locations are known a little bit, okay, not so much. And no matter how well you know this, it would be unreasonable to think that you can subtract out a million contributions to eliminate all of the noise sources from all of the asteroids, large asteroids that are there in the asteroid belt. Okay? So that gives rise to asteroid gravity gradient noise. This is the fact that the asteroids are acting on us gravitationally, and at some level that just becomes too big. So what we did was we actually used the NASA JPL small body database. If you'd ever told me 10 years ago that I'd one day spend time looking at rocks in the sky, I would have been like, come on, what are you thinking about? I'm a fancy theoretical physicist, but no, science is great. So we ended up looking at the small body database, downloaded it, whatever, and did a simulation, really, of asking, you know, what is the noise from the asteroids on these proof masses. And this is what we calculated. This is the characteristic strain, of course. And what you notice is that at frequencies below 10 to the minus 6 hertz, this sort of rapidly becomes very big. Okay? So the reason is the following. The asteroids are going around each other, going around the solar system, the inner solar system, with a frequency of around 10 to the minus 7 hertz, 10 to the minus 8 hertz or so, right? And that's where the noise dominantly exists. At higher frequencies, it just drops off very quickly. And we can even analytically understand why that happens. But so you see that it completely swamps whatever is happening at like low frequencies, 10 to the minus 8 hertz, 10 to the minus 7 hertz. So if your hope was to detect gravitational waves at 10 to the minus 7 hertz at interesting levels, as long as you're trying to do something LISA-like, okay, measuring the distance of two objects in the solar system very, very accurately, you can't do it. You're going to be swamped by this noise, right? You can either go to the outer solar system. We estimate you have to go all the way to Neptune and do it. Maybe that's possible. But it's interesting to ask, okay, what can humanity fundamentally do to solve this problem, right? And one day, we may want to detect gravity waves at 10 to the minus 7 hertz, 10 to the minus 8 hertz. Why not? What can we do as human beings to combat this noise? Okay? One option might be we send Bruce Willis and blow up all the asteroids. It'd be fantastic to do, but it's kind of expensive. So other things you can do. Other things that are maybe not quite as expensive, but still very expensive to do. So this is an effort to do something of that sort. Okay? But you could have stopped me and said, look, what am I talking about? I started off this whole presentation by telling you about nanograv, these pulsar timing guys. They've even found gravitational waves possibly, okay? I mean, there are claimed, I mean, they don't actually claim it. Some very interesting results have come out of that collaboration. So they're operating at 10 to the minus 8 hertz. Why are they sensitive? Why are they not being blocked by asteroid noise and all this other stuff, right? In fact, I even said I can't even do anything below 0.1 hertz on the ground because of the fact that the gravity gradient noise of seismic activity will couple on me and do terrible things. The reason why pulsar timing arrays work is because of the fact that they are not looking at proof masses, objects that are in the Earth. They're not even in the inner solar system. They're looking at extremely distant pulsars, things that are very, very far away. So when you're looking at something very, very far away, you notice that the effect of the gravitational wave gets boosted, right? It's h times L, that's what the separations go by. And now, effectively, you're looking at something that is a kiloparsec away. So effectively, the separation that you're getting is h times the period of the wavelength of the gravitational wave. It's something you've dramatically boosted your signal without changing the noise. And that is why pulsar timing arrays have the ability to go after really, really low frequency gravity waves, despite all the problems of asteroid noise and all these things, because the Earth, of course, is wiggling under all of this, right? But these guys are already at a planet scale experiment in terms of what they're trying to do. And if you look at their shot noise, it goes up. That's because pulsar timing arrays are fundamentally limited by the short noise of the radio pulsars that they're receiving, right? The pulsar outputs whatever output it puts out, and we're sitting on the earth and measuring it, and that's just what the Almighty has chosen to give us. So how do we go here? We can't quite do pulsar timing arrays, okay? And the main reason why pulsar timing arrays, of course, are working is because fundamentally pulsars are known to be stable clocks, right? The way these experiments work is that there are these pulsars going around. The pulsar is sending signals to you periodically, and you're sitting on the earth and you're measuring the time of arrival of these pulses. That's what you're doing. And this fundamentally makes sense because the pulsar is known to be a very stable clock. Its frequencies don't vibrate out of control at even at low frequencies. So let's ask this question. If I want to do something in the inner solar system, I can't do any local proof mass. Asteroid noise swamps that. I can only look at distant objects. What are other astrophysical objects out there that would have something stable enough for me to go look at, right? What are other things I could look at? How about the center of mass positions of stars? Okay, so stars are big objects and their center of mass presumably doesn't wiggle that much. So is it possible somehow that we can measure the center of mass position of a star accurately enough? Of course, I'm not going to sit out here and send a beam to the star and receive it back, right? Like I'm not going to do radar ranging from here to the star. So how do I think about making this measurement of the position of the center of mass? Well, what I can do is I can look at two different stars and measure the angle between them using some local instrument. And I can ask if that angle changes. If the angle changes, that of course is a measurement of the actual center of mass position of the star, right? So I can measure the distance or the position of the center of mass by an angle measurement. So here is the cartoon for that. I look at two different stars. I have a local detector, and this is the angle between them. Let's see what a gravitational wave does. A gravitational wave will pass over here between the Earth and this guy, nearly dominated by what's going on here, and that will change the path taken by the light ever so slightly, right? The gravitational wave will cause that light path to bend. As that happens, it will be the case that the angle that I'm actually measuring will change ever so slightly by an amount that is actually h, the amplitude of the gravitational wave. So for interesting gravitational wave sources, I have to measure strains of around 10 to the minus 15, 10 to the minus 16, which means I have to measure these incredibly small angles, right? Now, since I'm taking this as a futuristic thing anyway, right? I'm basically saying, look, if humanity is ever going to measure these gravitational waves, how would we do it? What kind of proof mass are we going to do? I'm going to first focus on whether or not there actually are even stable enough objects I can go and look at, right? Because with pulsar timing arrays, if the pulsars were not stable enough, there's no point anyway. So the question is, are there astrophysically stable objects that we can go look at for this particular thing? And then we can think about how expensive it is to measure this. So what's the challenge of stability, right? The main challenge is the fact that if I look at a star and I'm measuring its angle, right, between that star and another star, what I'm doing is basically looking at what I'm actually measuring in my experiment is not the actual center of mass. I'm actually measuring the photocenter, right? So because I'm collecting light from it and I'm using that collected light to actually figure out what position it actually is in. So what I'm sensitive to in reality is not the center of mass. I'm sensitive to the photocenter, the center of brightness, if you will, of the star. Now, if you have a star like the sun, the star will have star spots. So even if there is no gravitational wave, let's say I'm looking at two stars and there are these star spots that appear and disappear. If the star spots appear and disappear, that will change the photometric center of the star. And that means I would have inferred that to be a gravitational wave, even though it was not actually a gravitational wave. So how does that scale and what can we do about it? So if you make an estimate for what is the noise in the angle, okay, that the measured angle based upon some sort of star spot in the sky, in the star, it scales like the following way, okay? The angle error goes as small r over capital R squared times capital R over L, where small r is the size of the spot, okay? What fraction of the star is actually got this star spot? Capital R is the actual physical radius of the star, and then L is the distance between me and the star. So what you notice is that if you make capital R smaller, that is, you take a fundamentally smaller object, right? You can tolerate a larger spot size in it because the ability for a smaller spot size to change the brightness is limited. Okay? Similarly, the further away the object is, you can have a larger spot size in it. Okay? Both of them will cause the same angular error. So what this suggests, the very main fact that essentially I want to look at a small object so that I can be more tolerant of spots in it, makes you think about things like white dwarfs because they're pretty small. And in fact, here is a fact about the world, right? That a white dwarf rotates with a period of a day, something like this, or some of them are faster, some of them maybe a little bit slower. And we have sat and looked at white dwarfs, certain kinds of white dwarfs. And remember, what I'm interested in is basically asking, is the photometric center changing or not? So I can sit here on the ground and measure the intensity, just the intensity of light from a white dwarf, and ask if that intensity is fluctuating, right? Because if there's really a big spot coming and going, the intensity will fluctuate. So people have actually made measurements of white dwarf intensities using things like Kepler and K2 and things of this kind. And there are known white dwarfs, okay, whose intensity stability is better than 0.01%, 1 part in 10 to the 4. That is actually known, and they are anchoring something called the Land-Old standards, okay, that astronomers use. So, in fact, it is not like they even know that the thing is wobbling at 10 to the minus 4, that is just the level of their short noise limit. That's how well they can actually do it. So if I say, look, let me give you a class of white dwarfs that I've sat on the Earth, I've sat there and I've measured their intensities, I know that intensities are not fluctuating larger than 1 part in 10 to the 4, okay? How far away can they be so that the angle measurement that I'm making does not receive an error that is larger than 10 to the minus 16? If I do that, it turns out that if I find a sample of white dwarfs, okay, that are about a kiloparsec away, so still in our galaxy, kiloparsec away, and as long as their fluctuations in their intensity are no larger than 1 part in 10 to the 4, we know that the angle measurement that you will make from them will not be bigger than the 10 to the minus 16. The other advantage of white dwarfs is that there's another thing that can actually cause the center of mass position of a star to wobble, and that is planets, of course, or rocks, asteroids, things of this kind. One advantage of white dwarfs is that in the particular frequency band we're looking at, like, you know, something like a 10 to the minus 7 hertz, right? Whatever object is going around you, causing your center of mass to wobble, will have to effectively be at an Earth radius, something like this. Now, when a white dwarf gets to a white dwarf, it actually has gone through a period called the red giant phase, where the star will just eat up whatever is actually in there in the inner solar system region. So this should actually be a nice way in which a bunch of that region would be cleared of things like rocks and stuff like that. So you can actually be guaranteed likely that you have center of mass stability as well for these guys, okay? So this is my final slide, and after that I'm going to stop. Could you do this? What does it take? Okay, so if I want to measure a white dwarf that's about a kiloparsec away, and I want to basically get a angle sensitivity of 10 to the minus 16, what does it take? Well, you can essentially look at 120 nanometer light from the white dwarf, and you're going to use some kind of an interferometer in space. You're going to take, like, you know, something like 2 satellites, if you will, separate them by a baseline that's about 1 kilometer, collect the light with something like a 30 centimeter telescope on each side, and perform some complicated optical interferometry, okay, or really UV interferometry here. If you did all of that stuff, yes, you can in principle measure this strain of 10 to the minus 16. Now, I'm not going to make a comment about how technically easy or hard such a measurement actually is. What is true, okay, is that there are missions that people have proposed 20 years ago, things called stellar imager, okay? So these were proposed for other astrophysical reasons. And again, I mean, people did a bunch of work on them. I think there was NASA politics, all kinds of stuff. I have no idea what's going on. All I can say is that if humanity ever built such a mission, this would be a natural science case for them to do, right? They can just stare at a small number of white dwarfs for some time and use those to detect gravitational waves at those low frequencies. Of course, it is in fact the case that I use these numbers basically because the current limit on the intensity fluctuation of a white dwarf was 1 part in 10 to the 4. And that is, again, not a fundamental limit. It's not like someone actually measured the fluctuation. It's just that that's the level at which our current technology allows you to do. So, of course, if you were able to improve those measurements by building better telescopes or staring for longer and getting a better limit on the intensity fluctuations, that would, of course, mean that I don't have to go quite as far as a kiloparsec to see this, at which point, of course, this instrument may become easier to build. So with that, let me conclude. I think gravitational wave astronomy is here to stay. There's a very strong science case, I think, to probe the entire gravitational wave spectrum. It's extremely important to do. And I talked about how one may use atom interferometers to probe gravitational waves terrestrially, the frequency band from 1 to 10 hertz. In my opinion, there's a very strong case to think about asteroids as test masses as well. It really motivates, I think, measurements of asteroid seismology as well as space-qualified atomic clocks. And finally, I'm currently very enthusiastic about the fact that the gravity gradient noise from asteroids implies that if you really want to go to 10 to the minus 7 hertz or that frequency band, you really want to think about astrometry. And white dwarfs seem to be a pretty natural target. And should someone build something like a stellar imager, this becomes a natural science case for it. Even without me personally getting involved and doing anything, they could just actually just go and do it. So thank you very much.